Good evening. It's a pleasure to be here. I'm looking forward to all your questions. We're going to be talking about super heavy elements, and particularly the discovery of the two newest super heavy elements, element 115 and 117. And to give a brief overview of the talk, we're going to begin by what was really accomplished here. Synthesis of two new elements, that's important, but also decaying from those two new elements were 11 new isotopes, which are the heaviest isotopes of those elements ever observed. So there's really 11 new discoveries here, 2 of which were new elements. We observed decay properties and lifetimes that were consistent with modern theories of nuclear structure, and in particular with the shell theory, and evidence for the possible existence of something called the island of stability for superheavy elements, which I'll talk about a little bit later. These discoveries have to be officially recognized, and it took 5 years. The original work was actually done in 2010. A lot of confirmation work has been done since then, but in 2015, actually in January, at the end of the year, in the last day of December, the International Union of Pure and Applied Chemistry officially recognized the elements, which means that they can go forward and be named and go on the periodic table. And finally, we even have a new ice cream. I don't know if any of you have been to Razzleberry's, but on occasion, Razzleberry sells element 117 ice cream, and that's a lot of fun. I can assure you it doesn't have any element 117 in it, because element 117 only lives for about 40 milliseconds, so it's gone. So the outline is to begin with some historical context. Let's go back to see where the periodic table came from, and then where these ideas for super heavy elements came from. And then we're going to go into the discussion of the island of stability, onto the particular materials that we use for these experiments. And there's a real tie to Oak Ridge there, because those materials are only made in Oak Ridge, in our reactor and at our hot cells. What it really takes to make a few atoms of element 117, when you think about that, we're making one atom at a time. And so that's a lot of fun. And then finally, where are we going? So the periodic table began with Mendeleev's organization of the elements in these two-dimensional arrays. It was his innovation that said, what if we organize the known elements at that time according to their chemical properties? And the chart to the right there is actually his original publication of the periodic table. You can't quite read it, but what he actually did is he found an arrangement where you could predict the properties of the next element if you knew the properties of the element that you were looking at. And the net result of that was that he actually found gaps. And he predicted that new elements would fit in those gaps. And it turned out, I think he predicted something like 7 of them actually exist. So the person who drew the first periodic table actually used it to predict where new elements would be, and he was right 7 times. And that's an extraordinary innovation. And for that, he almost won the Nobel Prize. He came within 1 vote.
Wow.
And then later, the problem was that most scientists organized the periodic table according to the nuclear mass. And that didn't quite work out. And it was this guy, Henry Moseley, who in 1913 showed that it was the proton number that determined the chemical properties of the atoms. And he did that by observing the characteristic X-rays. And those straight lines there are actually the energy of the X-ray as a function of proton number. And you can see how linear it is. And he actually found two gaps for elements 43 and 61. These are the only two elements of the 92 that are radioactive and have short half-lives. And the result is that that they went away, and so they had to be discovered by other means. One of them, element 61, was actually discovered in Oak Ridge, and I'll say a little bit about that. But so this was the final work that finalized the organization of the periodic table, because now you knew how to organize it according to atomic number, not atomic weight. The tragedy is that Moseley also would have won the Nobel Prize, but you have to be living to win the Nobel Prize. And he went off to World War I and was killed at Gallipoli. And it was such a tragedy in Great Britain, where he was from, that they actually passed a law then that scientists could not be drafted so that they wouldn't lose them in wars. But he also would have won the Nobel Prize. So you come to the periodic table in 1939, and that's what it looked like. Element 45 had been found. Element 61 was the gap, and the periodic table ended at element 92. And so then in the work to synthesize heavier elements began actually in the 1930s with Fermi in Italy, when Fermi was in Italy. And he proposed to create transuranium elements heavier than uranium, by bombarding uranium with neutrons. Now, we know today what happens when you bombard uranium with neutrons. You get fission. But back then they didn't know that. So Fermi tried to do this, and he kept looking for something heavier than uranium in his products, and he missed fission. So he could have been the one who actually discovered fission, but did not. Then in the 1940s and 1950s, Seaborg at Berkeley and his co-workers, using their cyclotron at Berkeley, actually synthesized elements 93 through 103, and these are called the transuranics. At the same time in Oak Ridge, we knew about the missing element 61. We knew that element 61 was kind of around where fission products are, and we had the world's best supply of fission products because we had the graphite reactor. So two of our chemists, Jacob Marinsky is pictured there, and Larry Glendenin actually discovered the missing element 61 by doing chemical analysis of the fission products from that reactor. Seaborg couldn't figure out where to put his new elements because property-wise they did not fit in the way the periodic table. So he had to create this new row called the actinides. And he had to, what he did there is he took an original chart of the periodic table of elements as it was known at that time, and he cut it and re-put it together to make room for these elements. And so that illustration is what he actually did to show where they belonged. So now you have the periodic table from the 1940s to the 1960s with the addition of element 61, which was called promethium, which was discovered at Oak Ridge, and then all of the ones in green, which are the actinides, which were discovered by Seaborg and his colleagues. So now we come to super heavy elements. So a super heavy element is an element with an atomic number, with number of protons in the nucleus greater than 103. The existence of these elements, which are called transactinides, beyond the actinides, was first proposed by Seaborg in the 1960s, and the half-lives, range from hours 2 milliseconds as you go to higher atomic numbers. The first transactinide that was actually synthesized was done so in Russia at the Joint Institute for Nuclear Research in 1964. And you actually could go home and sit around your kitchen table with your kids or your grandkids, and you could figure out how to make super heavy elements. And what you have to do is you have to bring together two nuclei where the proton numbers add to the element that you want to get to. So the experiment that was done in Russia to make the first super heavy element was to take an ion beam of neon-22 and crash it in at high energy. These are energies in the range of 100 MeV or higher, into a plutonium-242 target. And you make a compound nucleus, and then that nucleus, to stabilize, emits a neutron, and you wind up with element 104. So plutonium has 94 protons, neon has 10 protons, 94 and 10 is 104, and that's basically how it's done. Now there's a little more that goes on there. You have to pick the right energy for the ion beam. You have to pick the right combination of beam and target so that you enhance the probability that that nucleus will actually survive. But in fact, from the point of view of getting young folks excited about science, they can sit there and they can make up their beams and their targets, and they can see what they would make in new elements. So why should we do this? It's hard work. It takes a lot of time, takes a lot of scientific infrastructure to do this. And the reason is it allows us to study the atomic nucleus at extreme numbers of neutrons and protons. And if you really want to understand something, the best way to do that is to push your knowledge to the limits. Go to the most extreme example possible. And these super heavy elements are just that. And they allow us to ask a number of questions. The fundamental question, how many protons and neutrons can be held together in the nucleus? At some point, there may be a limit. Nobody knows where that limit is. Can we develop a comprehensive theory that includes not only the lighter elements, which we understand pretty well, but these super heavy elements, which have different properties? Does this predicted island of stability exist? This is an island that we'll talk a little bit more later, but this would actually give us the ability to maybe even make new materials of elements that currently don't exist on Earth. And can we understand the physical and chemical behavior of elements with extreme numbers of neutrons and protons? When you get to these super heavy elements, the electrons are approaching velocities close to the speed of light, and so they behave very differently chemically. So the island of stability, again, first postulated by Seaborg, it actually has its origin in an analogy with the atomic periodic table. In the atomic periodic table, you have atoms that are more stable than others, and they're more stable because they have closed shells of electrons. For nuclei, you can have closed shells of both neutrons and protons. And those nuclei are called magic, and they have higher stability, they form more isotopes, they hold on to their neutrons and protons stronger than elements that are not magic. So in the same sense that you can predict the stability of an atom by knowing the electron configuration, you can predict the stability of a nucleus by knowing its configuration of neutrons and protons. Now, what this means is that the last stable element that we know of is lead. And one of the reasons that lead is stable is because it is doubly magic. It has a magic number of neutrons, a magic number of protons. Well, you can imagine the next element, which we've never observed, which would, by theory, would have the next closed shell. And that element will have an atomic number between 114 and 124, or 126. We don't know exactly where, and we're pretty sure on the neutron number that the neutron number is 184. So then you ask this question: if you could get there, would that element be stable? Would it at least have a very long half-life? And what we're trying to do in these experiments, it's more than just creating new elements, and that's a lot of fun just by itself. It's actually trying to get closer to that island and to see if the prediction of increased stability as you approach the island is actually true, and if we could actually get there, would we get these long-lived nuclei? So that's what this is all about. And so there is yes?
So how long is long-lived nuclei?
So nobody knows the answer to that question, but this slide might help. So because of the experiment that we did, we were able to make a very heavy neutron-rich isotope of element 113, which is shown right there. And the lightest element of 113 that has been made was actually made in Japan, and that has a lifetime of a fraction of a millisecond. The neutron-rich isotope, which has, I believe, 8 more neutrons, has a lifetime of 10 seconds. That is going toward the island. Now, at this point, you have to go another 8 or 10 neutrons to get to the island. But the lifetime has gone up by a factor of 40,000. So that would give you an idea, if that were to continue, that you at least might have 40,000 times more. You might have even more than that. So nobody really knows. It could be years, it could be hours, it could be millions of years. They might even be stable. And we won't know until we get there. But the likelihood that they are going to be long enough for us to do careful studies of these elements, if we can make them, of these elements and their chemistry, and learn a lot. But no, we're talking about lifetimes that you can actually work with, and possibly lifetimes that would be long enough that they would actually be able to be used. So in the 1990s, the Germans took over this field, and using something called cold fusion, they made an additional number of elements extending the table up to element 112. And cold fusion is the way you would think that you would do this. You bring two nuclei together at just enough energy to get over the Coulomb barrier. So you impart as little extra energy to the nucleus as possible. And you hope it holds together. And so they were able to do this, and you can see they used calcium and iron and zinc beams, and typically on targets, heavy targets like lead. And you can see that as you go from element 102 up to element 112, the cross-section is going down. So by the time you get to element 113, in your experiment, you're making 1 atom per year. Now, you can't run a research program on the hope that you might make 1 atom a year. The investment is too high. So the result is that around about 2000, we thought the field was over. The game is over. No one is going to run an experiment for 10 years to look for a new element, and we just didn't know how to go higher. And the breakthrough actually came in Russia around 2000, and using a technique called hot fusion. In hot fusion, you use actinide targets, which are naturally neutron-rich, so you have lots of extra neutrons, and you bring in a beam of calcium-48 and just it turns out that calcium-48 is one of those doubly magic nuclei. So it has lots of extra neutrons too. And that means it's more likely to hold together as you're crashing these nuclei together. The compound nucleus that you make is going to have lots of extra neutrons because you have a very neutron-rich target and a very neutron-rich beam. And that nucleus, it turns out, sheds that energy not by disintegrating, but by releasing extra neutrons. So you release 3 or 4 neutrons, and you're able to stabilize, at least for tens of milliseconds or more, enough to observe it, the new nucleus. The result of that was discovering 6 new elements, and they discovered 13, 14, 15, and 16, and then they discovered 118. Why didn't they discover 117? Well, to use this process, the hot fusion process, to discover element 117, you need a Berkeleyan target. Berkeleyan.
Oh, really?
Yes.
That's a bad boy.
Yeah. And the only place in the world where you can make berkelium is Oak Ridge National Laboratory. So here's a partnership made in heaven. In Russia, they have invested for decades in building the world's best infrastructure for heavy ion beams. And you need that to do this. In the US, we invested heavily in the capabilities of our reactor and our hot cells to do the production and chemical separation of berkelium. So that's how we got into the game. We got into the game because we couldn't do it alone, and the Russians couldn't do it alone, but together we could do it. And so the hot fusion led to 6 new elements, 1, 13, 14, 15, 16, 17, and 18. 50 new isotopes that had not been seen before. More than 300 decay chains, which means we made more than 300 atoms of these various elements. And the most important thing is that we extended the cross-section. It increased the cross-section by about an order of magnitude or higher, and the result is we could go higher. And the picture there is the academician Yuri Oganessian, who is our partner in Russia in doing this work. So now we have the periodic table in 2009. And in 2009, you can see we filled in the transactinides, which are the ones in light blue, and then dark blue are the ones that were done in Russia. And you can see the original actinide, you can see element 61, all of that is fitting together nicely, and yet you have another gap. So here's where Oak Ridge gets involved in filling the gap in 117. So what did it take? In the first experiment, we produced 6 atoms of element 117. You had to start with a calcium-48 beam. Now, calcium-48 in nature exists at about 0.5% abundance. So you have to enrich that. So we had to enrich it by about 500 times, and that was enriched at a lab in Russia called Sverdlovsk 45, which was part of the Russian nuclear weapons complex. Then you needed 20 milligrams of berkelium-249. That had to be produced here. And that was produced in 250 days of irradiation at the high-flux isotope reactor, followed by 3 months of chemical separations behind a meter of concrete, because it had to be shielded, to purify it to 1 part in 10 million. After doing that, we had to prepare the target foils in a way that they could survive in the ion beam. And so that was actually done at
Dimitrov in Russia, which is the kind of the Russian equivalent of our Haifa complex, but they don't have the capability to make berkelium. And then at Dubna, 150 days of continuous irradiation in the world's most intense calcium-48 beam. And the end result was 6 atoms of 117. And I'm going to try to convince you why we know that's real. Yeah, sure.
So when you make the berkelium,
yes,
is that done in the high flux part of the?
Yes.
I was just curious.
Yeah.
So you ran the target through there.
Yeah. So it's actually, it can be a byproduct of californium production, because you make berkelium when you make californium. You just have to do an extra chemical separation step to separate that out as well. But it's much less, but you make it the same time you can make it the same time you make californium. So this is the reactor complex at Oak Ridge National Lab. The large white building on the right is the high flux isotope reactor. It produces the highest thermal neutron flux in the world, built in 1966, never been surpassed. You need that to make something as difficult to make as berkelium. And then the buildings to the left are our hot cell facilities that allow us to remotely do these very important chemical separation experiments and purification. Because what comes out is 40 grams of mixed stuff that's very radioactive, and you have to chemically separate out the few milligrams of berkelium. So it takes a lot of expertise. And then in the reactor, this is just a view. It doesn't show up as nicely as I would like. The center, the kind of the blue thing in the very center of the picture to the right, that is actually the core of the reactor. Something about the size of a garbage can. 85 megawatts, 15,000 gallons of water per minute going through that to cool it. And that is where the very high flux occurs. And what's shown on the left there, those pins at the very middle there, those are fuel pins that are specially constructed to survive in the heat and neutron flux of the reactor where the material is actually irradiated.
So we're seeing Cherenkov radiation then?
Yes, the blue doesn't show up as brightly. It's really spectacular, but it doesn't show up here, unfortunately. And then at the hot cells, this is the process. This is really one of the really interesting types of green chemistry. You wouldn't think of this if you're working with these radioactive materials, but we start with 40 grams of americium and curium, and then we make targets out of that. We put them in the reactor. Then when they come out of the reactor 250 days later, we dissolve them. We do some ion exchange. And then at the last step, an anion exchange, which separates out the transcurium components from the original americium and curium, and then from that you can get berkelium, californium, einsteinium, and fermium. In the experiment that we did, we got 20 milligrams of berkelium, but you can see the lifetime is only 320 days. So we're talking about an experiment that's going to take a year, and you have to move quickly.
So you use what, gamma spectroscopy or something to identify them?
At this stage, yes, but to identify the elements, we use something different. Now, it's green chemistry because most of the americium and curium is left over, and so it goes right back into the next experiment. It's not wasted. So these are the names of the people who worked on an experiment. So this is a big deal experiment in terms of the number of people that's required to work together. So in Russia, that list; in Oak Ridge, that list; Lawrence Livermore National Lab, because we used them as a partner because they looked at the data at the same time that we did, and so we could see that independently we were coming to the same results. Vanderbilt University, we had some students from the University of Nevada on the team, and of course the people at Dimitrograd who made the actual target foils. And in addition to that, there were more than 50 people at Haifa REDC who performed the chemical separations. And so this was a wonderful example of international collaboration and work across boundaries in both laboratories. The result was this 22 milligrams of pure berkelium-249, and you can't quite see it, but if you look very carefully, you see a little green dot at the end of that glass vial. And that is what they were working with. That's what they got. And that is what they were manipulating, dissolving, and purifying behind 3 feet of concrete. And of course, if you drop it, you've wasted all of that work. They really did a marvelous job. Okay, so now it's time, you have your product, it's purified, it's ready to ship to Russia to do the experiment. It's decaying away with a 320-day half-life. And we have this race against time to get this stuff to Russia as fast as possible into the accelerator before it decays away. And it actually had some drama. So it was packaged, it was given to Delta with all the paperwork. Delta shipped it to Russia. It arrived at the Moscow airport. They forgot to ship the paperwork, so the Russians shipped it back. So the second flight over, it went with the paperwork, but it turned out that the paperwork had changed, and it was not the right paperwork. So the Russians shipped it back again. And then the third time, it went with the right paperwork, and it actually worked. But of course, our berkelium got lots of frequent flyer miles as a result of that. But it was amazingly still the fastest U.S.-Russia transactinide transfer of all time. And that is because at the scientific end, both sides realized how urgent it was to get this done. So there's a lot of pushing. Everything had to work. The Haifa operations, Haifa had to operate 11 on-time cycles. The processing had to be done right. The transportation had to work, and it had some drama, but with a few extra days, it actually worked. Target preparation had to be successful, and then the accelerator had to operate 24/7, for 9 months in order for this to go. And this is actually a picture of the cyclotron at Dubna, where the experiment was done. And on the right, you kind of see how it works. That the beam comes in from the left. It's a beam of calcium-48 ions. It hits the berkelium target. Some of the beam doesn't interact, and so that's bent off with a magnetic field. And so what goes on to the detector are ions that look like they may be compound nuclei. We don't quite know, but when they hit the detector, we know the energy that they hit by, and so that tells us, well, the energy is about right. Then they decay by emitting alpha particles. And so we look for a target-like particle that hits the detector, and that at the same position in the detector, you have an alpha particle emitted at about the right time with about the right energy. And then when that happens, they turn the accelerator off. So there's no noise, and you watch the subsequent alpha decays as it goes from 117 to 115 to 113 to 111, and so on. And you know from theory what the approximate lifetime should be, what the approximate energy should be. So for this to be a coincidence, you have to have an ion hit the target with the right energy. At that same position, you have to have an alpha decay with the right energy at about the right time. And then you have to have 3 or 5 subsequent alpha decays from that same place when the beam is off, with the right energy and with the right lifetime. And if you add all that up, in any case, it's 1,000,000 to 1 that this could be done by random events. And so we are very, very sure that we're right, and that is why the IUPAC eventually certified this as a new element. This is actually the energy spectra in the detector, and I won't go through all the details, but what you can see is when the beam is off, in the energy range, between 9.5 and 12 MeV, which is the energy range for these alpha decay particles, for the entire time of the experiment, that's the number of counts that we're seeing in the detector. So it's very quiet when the beam is off. And so we're very confident that we were seeing real signal. And so not only did we create two new isotopes, we created a new element, element 117. We created two isotopes of element 117. Those are the two pink boxes at the very top there. And then as they decay down to 115 and 113, 111, etc., you can see that all of those pink boxes are on the right end or neutron-rich end of the chart. So that's all new territory. So it's more than just two elements. It's 11 new heavy isotopes. So it's until it's officially named, it's called septium, which is for 117 in Latin. It's one of the two heaviest atoms ever made, the other one being atom 118. It was confirmed in Germany in 2014, again in collaboration with Oak Ridge, and the official recognition in December of last year. So here is a compilation of all the data. So what you see in the chart at the top is actually the alpha decay energy as a function of neutron number for the new isotopes of 111, 113, 115, and 117, shown in red, and the ones with open symbols are the ones that had been discovered previously. And look at how regular that data looks. So the 117 data lines up very nicely with everything else. The bottom is the half-life of those various isotopes of 111, 117, 115, 113. And again, you can see they are very regular. And so this preponderance of all of these 50 new isotopes that were made, all lining up in a systematic way, kind of in the same way that the periodic table lines up in a systematic way, is a strong evidence that everything is fitting together the way it should. And the reason that you have the low point there is that low point is right in between two magic numbers. The magic number at 162, and then the magic number that we're heading toward at 184. Now for the question about what the lifetime will be when you're at 184, well, look at those trends and look at where 184 is. And that is a log chart. There's a lot of room there for growth. So as we go forward, some of the isotopes that we're going to make are going to have even shorter half-lives. And so a very important part of this, to fill out the whole picture, to look at the lower neutron number isotopes of these elements, and also to look at their decay products, we're going to have to be able to go to sub-microsecond lifetimes. And we do that with these digital data acquisition systems. And it turns out that Oak Ridge is an expert in that area through our work in the physics division. And so we have actually been providing those detectors to Russia for doing those experiments. We send our nuclear physicists to Russia to participate in these experiments. So this is a collaboration that actually works between both countries. And not just one side doing one thing and another side doing their thing. We're all involved in all aspects of the experiments. And an interesting new experiment that we're doing. So we've kind of run out of targets. We can make the next target beyond beyond californium is Einsteinium. And Einsteinium we know how to make in microgram quantities, but not in milligram quantities. So we haven't quite figured out. So Einsteinium would be kind of a perfect next target. We haven't figured that out yet. But there is a special target that we could use. That's I think kind of a clever trick that we do. We have made at HIFER over the life of the reactor so far 8 grams of californium. This is an element that does not exist on the planet. So we've made 8 grams. That's a lot, actually. And it's used for medical purposes. It's used in industry. It's used in a variety of various applications. All reactors are started up with californium sources, for example. Well, it's californium-252 that's used for that, because californium-252 is the isotope that is a very big neutron producer. It's very radioactive, but it has a half-life of only 3 years. A lot of that was produced 30 years ago. A lot of those sources have now come back, and we just store them. We don't quite know what to do with them because they're not useful for their original purpose as a neutron source. But as they decay, they become enriched in californium-251. And californium-251 has a much longer half-life. I think it's around 1,000 years, or some range like that. Now, if we could separate that out, we could create a target that has a mass of 251, the most neutron-rich target ever made. The original element 118 experiments were done with californium-249. Because no one had, the only way you're going to get to californium-251 is the decay of the californium-252. So we took those old sources and we chemically purified them, and we made a target that was rich in californium-251. And now that's the next experiment that's going on in the Dubna right now, is taking and using the californium-251. What previously we kind of thought was waste actually is enormously valuable. And so it's great that people did not throw away the old californium. And those experiments are ongoing right now. And we're actually, because we have 2 more neutrons, californium, the original material used was 249. We're now using californium-251. That is a difference of 2 neutrons. Because we have 2 more neutrons, we can make heavier isotopes of 118. That brings us 2 neutrons closer to the island. And so that's the experiment that's going on. It's been going on now for about 4 months. We've made 1 atom so far, so we don't think we have the energy quite right. There's some tweaking that has to be done. But the net result is that we will make the 2 heaviest nuclei ever made if we do this. And we will get, for the even elements, we will get 2 atoms closer to the island. For all elements, we'll get 1 atom closer. And that, you know, we'll see, do we get another factor of 10 in lifetime by doing that? And so this is the picture today. That's all what you see there, with the exception of the few yellow boxes on the far left. That all did not exist in 2000. All of that is new. And you can see where we are up at the top. The 2 kind of pinkish colored boxes are 117. We were credited with the discovery of 115 because 117 decays into 115. We weren't trying to make 115. And now the purple, light purple boxes are experiments that we're trying to do right now. One is this experiment with these with this leftover material from the old californium work, the work with the 251 isotope of californium. So that's one. Another one is work to the left, where we're trying to make lower weight isotopes of these super heavy elements to try to connect them to the nuclear mainland. So that's one of the reasons why we need these sub-microsecond detectors. And then at the top are all the new things that are on the drawing board. For example, if the next beam that you could use to make super heavy, I mean, one way to do it is to go to heavier targets, but we kind of run out at California. Well, we can go to heavier beams, and titanium 50 is the next beam. And so we're doing work there. That could get us to element 119. If you then used the titanium beam instead of with the Berkman target, with a Californian target, you get to 120. If we could ever figure out how to make enough Einsteinium, you get to element 121. That's all we can do right now. We don't really have a clear path to go higher than that. But all of this is within the realm of possibility. So we would have to figure out how to make even better targets of californium-251. We would have to figure out how to use titanium-50 beams and whether you could actually get the cross-sections that you need. And we'll have to figure out how to make more Einsteinium. So the next steps. Experiments are being performed in Dubna right now using the californium-251 targets, and we're working through that. Future collaborations are going to be done at a new facility that's being built in Russia right now called the Super Heavy Element Factory. And this will have a cyclotron with 10 times the beam current that we have now. Now we can do even lower cross-section experiments because we will have better detectors and 10 times the beam to work with. And that's just a picture from last winter of the Super Heavy Element Factory under construction. And below there is a picture of the cyclotron that was delivered in November there. Now, it's interesting that the cyclotron came from Ukraine. So you have this big problem between Russia and Ukraine going on along the border. At the same time as that was going on, this cyclotron was shipped by train across that border. And that's a very interesting thing, that that was actually able to be done. And one of the reasons is because countries realized from the Cold War that the only communication sometimes that they had was between the scientists. And the answer is the Russians in no way have pulled out of their collaboration with us on the super heavy element for precisely that reason. And we have not pulled out either, although we have to go through a lot more State Department approval and that sort of thing, but we get the approvals because people want to keep the communication open. And so, in summary, 2 new elements with atomic numbers 115 and 117 have been officially discovered. These are actually the second and third elements discovered at Oak Ridge, the first being element 61. And of course, all 9 of the new elements were actually discovered using isotopes that came from Oak Ridge. We have 11 new heaviest known isotopes that have been observed in the decay chains from the new atoms of element 117 that we've made. And they show a general trend toward increased stability. And to answer the question about what the lifetimes might be, we're confident the lifetimes are going to be long enough to do chemistry studies as well as nuclear physics. And finally, a consistent picture of nuclear properties for heaviest nuclei is emerging. The critical role of nuclear shells in adding stability because they wouldn't survive otherwise. Experimental verification of the effects of the island of stability. We know the lifetimes are going up substantially. We just don't know how much because we haven't got there yet. And most important, this could not have been accomplished without international collaboration. And this is just an example of the power of what can be accomplished if you work together across national boundaries. So that's the presentation. Thank you very much, and I'd be delighted to
That's very good. You don't really detect your creation. to detect the demise of the new element.
That's correct.
Very sensitive radioactivity.
Yes, yes.
Do you have any worries as you get to the island of Sudan?
Yes.
Suddenly it doesn't work.
We don't know how to. So if these did not decay, we would not know that it happened. What will change as the lifetimes get longer? If they get into that range where we can't wait long enough for them to decay, we will do the detection in an ion trap, where you can detect an individual ion at a time. And so that is actually being worked on now. There's a new type of detector called a gas catcher that actually allows you to do that. And so that technology is being developed in case we get into that precise problem. That was an excellent question, very observant. So some of that work is being done in Argonne National Lab. Some of the work is being done in Russia at Dubna, and some of the work is being done at Texas A&M.
Nice thing for antivirals.
Yes, yes. Yes, sir.
Back in the 1980s, I was asked to design and have built a detector to find transuranics in the Earth.
Okay.
I think they had ran it probably a year, but they never found anything. And I was wondering if you know at what mass spontaneous fission stops.
Well, I don't know, obviously these could be counterexamples if they are. These eventually, they decay by alpha emission, and then at some point you have a fission. At the end, those chains all terminate in fission. So we haven't defeated fission. Yeah, we haven't defeated fission. But the question then becomes, how long does it live? The reason that we did, so we have looked, the question is really, do we have super heavy elements in nature?
Yeah.
And so we have looked with very sensitive mass spectrometers for super heavy elements in meteorites, for example, which are very old. We've looked for them in very old rocks on Earth, and we haven't found any. And there are two reasons for that. Either they're not made in stars, and so we're making things that have not previously existed in the universe, or if they are made, the half-life is very short compared to the lifetime of the universe. And that still leaves a lot of time for a long lifetime. But the experiments that you were doing then, you actually see a few transuranics on the planet. For example, in South America, South Africa, there was actually a natural nuclear reaction that occurred, and that produced a few. But in general, we're talking about things that we don't find
I've seen one report
on the planet.
of plutonium-244 found in a deep sea sediment
Mm-hmm.
by Australia.
Yeah.
I haven't seen the report yet.
Yeah.
Just in the news.
Yeah. But it's a very good question. We've looked kind of to the ability that we can, and we have not found any in nature yet. Any other questions? Yes.
You haven't named the new element yet. What is your suggestion?
Okay, so one of the great privileges that you get when you're on a team that discovers a new element, in this case it's fortunate it's several new elements, is that once the discovery is validated, you are asked to suggest names. Now that doesn't guarantee that the name will actually be chosen, but typically it will be if it's not a name in conflict with other names or that sort of thing. So I can't really answer that because we are sworn to secrecy on this. We can't talk about this until the names are actually officially posted by the IUPAC. But I can tell you that if you look at the names that came out of the Berkeley area, you have Berkelium, you have Livermorium, and you have Californium. So you can kind of guess that it will kind of be in that range.
Yeah.
New building.
Any other questions?
Who's the biggest collaborator? What international country is Russia the biggest collaborator?
Russia, by far. I mean, Oak Ridge and Russia were key to this experiment. This experiment could not have been done without Oak Ridge. None of these experiments could have been done, and could not have been done without Russia. And so the biggest investment in human capital, in research infrastructure, both in Oak Ridge and in Russia. The nuclear physics team at Lawrence Livermore Lab was very important in providing an independent assessment of the data, because we wanted to make sure that we hadn't missed anything. And then we had partners who collaborated with us from Vanderbilt, later from the University of Tennessee, and also from a few other institutions.
Great.
Yes?
Earlier in the talk, you mentioned that these elements have, their electrons will be relativistic.
Yes.
Actually, more than hyper-relativistic.
Right.
And I immediately thought of elements that we already know are very stable, like silver, for example, where the outer shell electrons are clearly relativistic. So I'm wondering, in what way are these elements different chemically because of that relativistic effect than, say, something like silver?
Well, one of the changes that occurs is that the size of the atom changes, so it has an impact on the size of the atom. The other part is that typically you get more overlap between, you get better separation of the electrons in conventional nuclei than in these very heavy nuclei, with the result that the chemistry that you might expect won't be the same, because the F electrons won't be kind of where you expected them to be, or that sort of thing.
Okay, great, thanks.
What would be your best guess at the half-life of the area around 184?
So we do not know, but of course we know a lot more now than we knew before these experiments were done. And based on the trends, and my expectation that the island won't be precisely at 184, but will be spread out for effects kind of like what you were talking about, I think it's going to be in the range of years. But it could be much less, or it could be millions of years, and there are some people who say it could be stable. So we just don't know.
So if it's stable, can we call it stability?
Well, you know, it turns out, for those of you who saw Avatar, they had unobtainium.
They did.
And this is close to unobtainium when it talks about 2 years of experiments with millions of dollars worth of infrastructure to get 6 atoms.
I have something for you.
Okay.
And we'll get a picture. I'll shake your hand.
Okay, thank you.
And I'm going to present you with an Orion mug.
Oh,
And you can smile.
I will treasure it.